Hi, folks. Dr. Cole here. Let's do our lecture on regression, part 2. Okay, make this just a little bit bigger. All right, so what are we doing here? Now we're doing linear regression with multiple variables, which is called multiple regression. Multiple regression is a powerful statistical technique that helps us understand relationships between one dependent variable, that's our y variable, and multiple independent variables. Those are our x variables or our predictors, right? The dependent variable is the outcome variable. The independent variables are the predictors. We're trying to see how do these x variables predict the outcome variable, predict the y variable. So essentially, this extends what we did in part 1. It extends the simple linear regression, which involves only one predictor variable, to include multiple predictors, allowing us to see how several factors simultaneously influence an outcome. So you see here, we're also using the word factor as a way, as a name that's synonymous with independent variable or predictor. So we're sort of saying like something is a factor of something else. The outcome is a factor, or the outcome can be predicted by multiple factors, multiple variables. Multiple regression is similar to the two-way ANOVA that we previously learned, which is a hypothesis test of the relationship between a dependent variable and multiple independent variables. In ANOVA, we needed the independent variables to be factorial variables, that is, categorical variables. But in regression, we can use the continuous data. That is, we can lead, just like we learned in the last lecture, the predictor can be all of the data. Doesn't have to be categorized into low and high or low, medium, and high, or some manageable set of factors. Now, just like we learned in the last lecture, we can run the regression with categorical independent variables in R or JASP. We're using JASP. And as you know, JASP was built on R. And we will practice a few examples. So let's go ahead and look at some key concepts in this lecture. So the regression equation in a multiple regression, we're still doing the y is a function of a plus bx, but now we have multiple b's, right? We have multiple betas, and because each beta reflects the slope of each predictor, each independent variable, each x. So y is our outcome variable. That's our dependent variable. That's what we're trying to predict. X1 and X2, etc., are the independent variables, our predictors. A, or really, if you think about it, A is the beta when all of the x's are 0. So sometimes we think of A as beta 0. And that's our y-intercept, right? That's the predicted value of y when x is 0. So it's where the line crosses y, where y is and when the line crosses when x is 0. And beta 1, beta 2, etc. Those are our coefficients. That's the slope. That's how much we're predicting is going to be a change in y for each independent variable. So a reminder about these coefficients. Each coefficient, or beta, represents the change in the dependent variable for a 1-unit increase in the corresponding independent variable x, assuming all other variables are held constant. And remember, we can ask for the output to include both the unstandardized, which is the actual change in Y in the units of the variables, or we can get an output that also includes the standardized beta, which standardizes all of the coefficients so that you can sort of look at them holistically comparing to each other, and you can see how they relate to each other in a standardized unit. So assumptions, multiple regression analysis rests on a few core assumptions. Again, we're talking about parametric statistics. So this is normal distribution, that our residuals are normally distributed. We're also talking that we're assuming linearity. The relationship between each predictor and the dependent variable is linear. It may be nonlinear or curvilinear, and we can test for that. That's more advanced analysis. I'm not having you do that in this lecture, but I'll direct you to a video where you can learn how to do that. Independence, observations are independent of each other. Something called homoscedasticity, which is that the variance of the residuals is constant across all levels of the independent variables. Another key term is goodness of fit, which is, we learned about R squared in the last lecture. That tells us the proportion of variance in Y explained by the predictors. A higher R square indicates a better fit. So that's another way of thinking about R squared, which is helping us understand the effect size in the linear regression. It's also what we call a measure of the goodness of fit. The higher the R square, sort of the better fit of all of these group of predictors. And we're going to be looking closely at the R square as we add in more predictors, because it may be that the predictors don't add anything to the goodness of fit. And so we can describe that and then say, since a predictor doesn't add much to the model, we might as well not have it be there. It's not helping us with any type of prediction. Statistical significance in this concept, in this analysis, is that we're looking at the p-value for each predictor, and we're going to be looking at getting into an example of something called hierarchical analysis. Think about it like this. Hierarchical analysis and multiple regression is an approach where predictors are entered into the regression model in a specific sequence or hierarchy that we choose as the statistician, allowing us to assess the incremental contribution of each set of variables. It's particularly useful when we have a theoretical or practical reason for ordering predictors, such as assessing the influence of specific variables while controlling for others. And we'll be practicing that. Predictors are entered in steps or blocks, and each block contains one or more variables, and the order in which blocks are entered is determined by us as the researcher, the statistician, based on theory or logic or other empirical considerations. By adding the predictors in the blocks, the hierarchical analysis allows us to see how much additional variance in the dependent variable each new block of predictors explains. What do we have that's our measure of the amount of variance that's changed? Well, that's R squared. R squared is the amount of variance that can be accounted for, right? It's the proportion of variance in the Y explained by the predictors. So we can look at the incremental change in R squared, called delta. R squared delta typically refers to change of, so this is delta R squared, which is the incremental R squared after each step, which will show us the additional proportion of variance explained by the new predictors over and above the previous model. And we will start with model 0, which is our null model, and we'll practice that. Some other terminology, I'm going to teach you about flex plot. You've already practiced generating that, I believe, in the last, in part 1, but, you know, fitting the best fit line in a regression is going to be a linear, a straight line. With FlexPlot in JASP, we can use a little more sophistication of a type of best fit line that is called locally estimated scatter plot smoothing, or LOESS. And we'll see what that looks like in our example. And so what is it? It's a smoothing technique. It fits multiple regression lines to subsets of the data, creating a flexible, smooth curve that captures the general trend in the data without assuming a strict linear or specific functional form. Instead of one straight line, for example, as in if we were to plot the best fit line, it's going to be a line, it's linear regression. The flex plot, if we use the LOESS, adapts to the shape of the data, making it particularly useful for detecting nonlinear relationships. Well, if a line is a straight line, nonlinear, it might be a curve, it might be a U, it might be an S. All of that is what we call nonlinear. I'm not having you do that in this lecture, but here's a great video that I recommend if you want to learn more how to do it. It's really not that complicated. And then finally, in leveraging basically the concept behind hierarchical analysis, but doing it in a way that asks JASP or R to decide what order should multiple predictors be entered into the analysis that best optimizes the model, we can use a technique called stepwise regression. It's a technique for building regression models by automatically adding or removing predictors based on specific statistical criteria. In this case, we will see when we get into JASP, but think of the criteria as if it's not significant, if adding the predictor is not improving the model at some level of significance, then we won't add it. And it's happening automatically. It's commonly used to identify a subset of variables that provide the best predictive power for the outcome variable, while also potentially excluding irrelevant or redundant variables. There are different strategies or techniques in stepwise regression, and we're going to use the technique called stepwise selection, which is called a bidirectional technique. It's combining both adding variables from the beginning and then also maybe from the bottom to the top, sort of backwards. And then variables are added or removed iteratively. Iteratively means it just keeps trying. That's iteration till you get the best model based on whether they meet the inclusion or exclusion criteria. The process stops and no more predictors can be added or removed. Stepwise regression can be particularly helpful as an exploratory tool. We don't know that's what exploration means. We're just going to see what we get, especially when you have a large number of predictors and limited theoretical guidance. However, it's generally recommended to use step regression carefully and complement it with theoretical insight or other methods, such as hierarchical analysis or hierarchical regression. Probably best that we call hierarchical regression analysis. Okay. What else? Oh, it's important to check assumptions of the regression. Whether or not you do anything, if you find some violations of the assumptions, is another story. But this, at least, when you check the assumptions, you can make some qualitative statements as the statistician, and it helps you to put some qualitative language around how confident you are that the results of the regression are accurate. Maybe accurate's not the right word, but again, we're being very careful as statisticians. We never, which is why we're using hypothesis testing, because we're never saying without a doubt I'm 100% confident. We always have some level of possibility that the results might not be valid or the statistic might be rejected, right? That's why we have the p-value. The p-value is giving us the probability that we might have made a mistake, which is why a p-value that is less than 0.05 is considered statistically significant at the 95% level of confidence, which means we're confident that 95 times out of 100, we would find these particular results if we repeated it over and over again. That's what it means. And by checking the assumptions of the regression, we could add even more qualitative statements to the p-value. So I'm going to teach you how we check through visualization the assumption of linearity, the assumption of normality, and the assumption of homoscedasticity. And the particular examples we're using today, we're not necessarily concerned with the assumption of independence. That's more applicable to data sets where maybe one of the predictors is multiple time points. So we're not going to practice that today, but there is a statistic that's available in JASP called the Durbin-Watson test that is checking for something called autocorrelation. So we're going to use the same data that we used in the last lecture, the LMAPI2 data, which is the data on the elementary school performance, right? The academic performance index. So elementary school academic performance index from the year 2000. And we have all these predictors. And so in our first example, let's practice a multiple regression where we are regressing API on year-round mobility and year-round times mobility. So let me review what I just said. So API is our Y variable. And the way we think about it from an equation is regression is always Y regressed on X, right? Y is the outcome variable. In this case, the outcome variable is academic performance in the year 2000. We're regressing it on our independent variables. We're regressing it on our X variables. And in this case, we have two X variables, year-round and mobility, but we're also going to create an interaction term to see if there's some interaction, some significant interaction that is occurring. So the three things that we'll want to generate are the correlation between all of the variables. We'll practice the flex plot, and then we'll do the linear regression. That's our first example. And then in our second example, we're going to regress the academic performance on the set of independent variables that basically reflect parent education, whether the percentage of parents who do not complete high school, the percentage of parents whose highest education is high school, the percentage of parents whose highest education is some college, the percentage of parents whose highest education level is college graduate, and the percentage of parents whose highest education level is graduate school studies. So we're basically going to do Y on 1, 2, 3, 4, 5 X's, 5 predictors. And we're going to use stepwise to help us explore which of these or in what order should they be if we want to have the most prediction in step 1 followed by sequential models. And are all of these significant? Are some of them not adding anything more to the model? And that's what stepwise will help us. All right, so let's go ahead and start. All right, let's get started. And I'm going to write this down so I know what I'm doing here. We've got API on year-round mobility and then the interaction. Okay. Then we want to make sure that we start with correlation and then the flex plot and then we'll do the hierarchical. Okay. So here's JASP. I just opened up the data. Okay. So let's go ahead and start with the correlation. Oh, you know what we're going to do? Well, we might as well remind ourselves what year-round, we can see year-round is a categorical variable. So let's just remind ourselves what we're looking at here with year-round. So year-round 0 is it's not open year-round, and 1 it is open year-round. So we can leave it at 0 and 1, or we can just make our life a little bit easier. And if it's 0, it's a no. If it's 1, it's a yes. And then when we do the analysis, it just might make it a little bit easier. All right, so let's start with the correlation. And now we're going to, gives us an opportunity to practice multiple correlations. So we've got API, we've got year-round, and we have mobility. So we want to report the significance. We might as well flag significant correlations. Let's create the visualization, which is the scatter plot. And then let's go ahead and add the densities and the statistics and the confidence intervals. Okay. So it's rendering. See that it's running the analysis here, and now our visualization appears. So we see from our correlation matrix, the correlation between a variable and itself is, we don't do that. So that's what that's why there's no values there. But now we see that API, the outcome variable, is significantly negatively predicted with year-round, right? If as it goes from not being opened year-round to 1 to being opened year-round, then we have a large drop in academic performance. I think we talked about that in the last lecture. That's because if schools are open year-round, that really means that kids need to be going to summer school. They didn't make it through the school year. So their academic performance was not well during the school year. And it's flagged with 3 asterisks, which means that's a very significant correlation. It's significant at the 99.9% level of significance. And then the correlation between the outcome variable, academic performance, and mobility is also negative. And let's remind ourselves what mobility means. Mobility means percent of first year in school. So that's the percent of, so mobility is the percentage of students who are in school for they're new students. It's basically an index of how many students are new. So if you think of new kids coming in and out of a school district or immigration issues, a lot of new kids coming in and out of the school district, that's going to perhaps disrupt academic performance. In fact, that's what we see, right? As the percentage increases, API drops down. We have a negative correlation. And then we've got this visualization. So this is the density, this is the distribution of our academic performance. And then we see that the correlation between API and year-round is negative 0.475, and the correlation between API and mobility is negative 0.206. And then we see the distribution of each of these variables, API, year-round, and mobility, as well as some of the interaction slopes. So we have API and year-round and API and mobility. But these are a little bit kind of a little bit little bit abstract, but we see, so overall, right, API is declining. We're seeing that negative slope as mobility increases, right? So API is on the y-axis, right? So academic performance is decreasing as we go from 0 to 1, from not being open year-round to yes being open year-round. And we see that academic performance is decreasing as we increase the percentage of students who are coming into the school for the first time. And the dashed line is showing us that 95% confidence interval around predicting that best fit line. Okay. Now, how do we put it all together, though? Is there a way that we can plot all of these three together? And that's where the flex plot. So that's under descriptive statistics, flex plot. So that would be next. And what we're going to do here is we're going to add API, that's our dependent variable. And let's plot mobility. So already now we can sort of see, and what we've done in the options is we've asked for that smooth fitted line, right? If we were to change the line to regression, it would be the same line that we see, the same scatter plot that we see up here when we're looking at API and mobility, right? It's the same line with all of the, here's all the points, and we have the same thing. There's the same line, okay? But if we make the line be smooth using this smooth fitting LOESS, we it helps us visualize a little bit better what's happening. Let me make this smaller. It's helping us visualize if there is some sort of nonlinear relationship. And we see here a very strong linear relationship, but then as the percentage increases, we have these scores that are outliers. There's a few school districts or a few schools where they have a high percentage of new students and the academic performance is quite high. Probably not enough for a nonlinear relationship because there's just not a lot of data here. Now, how does this relate to year-round? Well, we could also, if we got rid of mobility and just did a visualization of year-round, we're going to see the relationship visually between academic performance and year-round, which is this, right? And the regression line between those two is not able to be plotted here, but a estimated regression line is what we would see here. So we can see that the flex plot doesn't really give us a best fit line when we have categorical variables. But what we can do is we can say, well, let's put the year round as a panel and let's add our continuous variable mobility as the independent variable. So now we have a plot of mobility for when the school is not opened year round and a plot of mobility for when the school is opened year round. And if we made it the smooth fitting, we can start to see what's happening from any potential curvilinear relationships. So what we see here is when the school is not open year round and we're looking at mobility, as the percentage of students increases who are first year students, the academic performance drops for schools that are not open year round. But when schools are open year round, look what's happening. Now we're starting to see this upswing as the percentage increases. Now, What could that be? That could be, well, this is maybe these are the kids that are going into summer school, and maybe this is showing us the value of summer school. So those kids come in, maybe they're not coming in the fall semester. Maybe their mobility is they come in the middle of the school year in January or February. So they stick around for summer school, and you know what? Then their academic performance increases. That's This is a pretty cool way of visualizing that. And that could be one interpretation. Because the school is open year round, those kids that the higher percentage of those kids that are coming in later, or it's the first time joining the school and they couldn't join right away in the fall, they get to take advantage of summer school and their grades improve. All right, so now we can let's now do the regression. So linear regression. And our dependent variable is going to be API. And this method is where we get into the stepwise piece. We're going to do that in a minute. Let's just put them all in at one time. We're not stepping them in any order. And let's do year round is the factor, and mobility is the continuous variable. And so when they're all in together, we see that these two variables are accounting for about 26% of the variance, right? R squared is the proportion of variance accounted for by your predictors. So we are predicting academic performance predicting about 26% of academic performance by just these two predictors, and they're both significant. And now the question is, but is that interaction that we see here, is this really something that is significant? Is there something significant about year-round and mobility that can be really meaningful, or is this just what we're seeing visually because of a few outlier points? That's really the question. That's why we want to do, in our model, we want to do a year-round times mobility interaction. So one of the ways that we can do it is we can now add another, we'll do a plus, we're going to add another model. And in this model, we're going to click mobility, hold the shift button down, click year round. So both of these are selected, and then bring them into the model, and you can see it. That's how you create the interaction term, mobility times year round, right? And in fact, we really don't need model 0 in this case, because model 0 is just without any predictors, but it's fine. We can just leave that. It's okay. So now what we want to do is we want to, in our statistics, we want to make sure we click on R squared change, and then we want to click on F change. And then under the plots, we want to click on the what I had said here that we would do when we're looking at the assumptions. We're going to look at the plot of the residuals versus the fitted values, and the QQ plot of residuals. Okay, so the residuals versus the predicted, and the QQ plot. Right, so here are the two visualizations that help us with our assumptions. The residuals versus fitted is another way of saying residuals versus predicted. So that's what we plotted. So let's go ahead and go through all of this, and I'll help you understand what we did. So from the top, there's our correlation. Next, we did our flex plot, and now we have our linear regression. So it starts with the model summary, which is the goodness of fit. It's showing us how these models are changing as we added in variables. So model 0 was no predictors. In fact, you know what? Why don't we, let's do one other thing. Let's tweak the model. Let's add one more model, and in this model here, let's get rid of the interaction term. And in this model, let's get rid of mobility. So now we've got mobility and year-round in model 2. So model 0 is nothing. That's just the no predictors. Then we add in year-round. Model 2 or block 2, we're going to add in mobility. And then in block 3, we're going to add in the interaction term. Are you seeing what's going on? Okay. We really don't need model 0, but I'm showing it here for demonstration purposes. Okay, so now we have these basically 4 models. In model 0, there were no predictors. And now as we added in year round, and you can see the note here, M1, as we added year round predicts 22.9% of the variance. Adding in mobility, we see that the R-square increased by 3.6% to 26.5%. And that change, the change in F, was or is significant, right? The p-value of this change in F between model 1 and model 2 is significant. And then in model 3, we added in the interaction term, and that added in 2.5% of a change in R, so that now we predict 29% of academic performance. And we also see that the model improves. It's a better model. And that's what, when the p-value is significant, that's saying that adding predictors is suggesting that the model is better. This ANOVA table is just what the overall model is, what at each step. So by the time we got to model 3, overall, it's still a significant model. And this change in F from 71 to 53.575, which is 13.683, that's significant. Okay. Now, the actual regression coefficients, well, here they are. So we see that in model 1, year-round is very significant. The beta is, excuse me, negative 161.29. And then in model 2, when we added in mobility, now year-round is still significant. It's a beta of negative 159.06, and mobility has a beta of negative 3.61. We see the y-intercept keeps changing because we're adding in more shared variance. There's more things that are predicting academic performance. And then finally, by model 3, the mobility, the year-round is a very strong predictor. Very big change in academic performance, 290 points if the school's open year-round. The academic performance drops by 5 for each percent increase in mobility. And then the mobility times year-round interaction, Remember, we saw that's that slope going back up. That's why it's a positive. So when we put it all together, we would say that, and then let's address the assumptions. So over here, what we're looking for is we're just looking for a random scatter, and that's we have a random scatter. We don't really see any type of pattern, so we're feeling pretty confident that we don't have any problems with linearity or homoscedasticity, which is that there's basically equal change, equal spread of these residuals across all of the predicted values. There's a few strange things, and that's also reflected by the fact that on the QQ plot, ideally you want the residuals to be plotted along the line. And so some on the low end and the high end, we have some outliers. And that's what we saw here, right? On the low end, we had a few outliers, and then over here we have a few outliers, and so that's being reflected here, but generally it's fitting very well. It doesn't suggest that we really need to transform our variables to perhaps log values. So then what would we interpret? Well, we would say that this visualization is probably pretty accurate, that when the school is not open during the summer, we have a strong decline in academic performance as the percentage of kids come in who are coming into school for the first time because they've moved there, they've moved to that new school. But there are going to be some percentage of those kids moving in that maybe have good skills. They've got good knowledge. They learned a lot in their previous school district. So it's not an equal drop. And in fact, when those kids that come in and have an opportunity to continue the school year, some of them are performing very well. And this, in fact, is significant because we see that the interaction term, year-round times mobility, is a significant interaction term. And from a model perspective, adding that interaction term to the model is significant. So that's how we would interpret this. Okay. That's part of our job as statisticians, is to go through our analysis and tell a story. So I hope this was a story that makes sense to you and that you can do the same in your assignment. Now, the next piece, the last piece, was to say, well, let's do a stepwise and find out, are all of these 1, 2, 3, 4, are these 5 predictors all significant? Do they add value? Should there be a particular order that helps us understand the relative strength of adding each one? So we'll use stepwise for that because we're purely exploring. We don't have any assumptions. That's really what hierarchical allows you to make assumptions. Now, I will say where hierarchical is particularly important is, let's say that we wanted to, now that we check mobility, let's just say we wanted to control for year round. We want to keep year round as a constant. And now we're going to try some other variables. Okay, so let's say that we tried another one, like meals, percent of schools that need meals. Well, again, we would want to make sure that year round is alone in a model. So by having year round alone in a model, subsequent models now are looking at the relative contribution of that predictor while controlling. So if model 1 was where we added year round, and usually then if we're talking about controlling, we tend to think of model 0 as that starting point. So really what we would want to do is we would want to say, we'll get rid of some of these models. So now, and we can just drag these in. So model 0 is the starting point, and then we'll add meals in model 1. So now we have 2 models. So now we can say, for example, that in model 0, which is our year round, which we already knew was 22.6% of the variance, controlling for that, when we bring in meals, now we see that we are predicting almost 60%, right? Because that's that R squared change. The total R squared now with year-round and meals is 82.3%. That's as if we're saying controlling for whether schools are open, whether schools need to be summer school or not. As the percentage of kids come in that need meals by the school, we are able to predict an additional 60% of the variance. Now, if we plotted that as just an example, we can see what that looks like. So let's stick with year round and that panel, and now we'll put meals. And this is just another example for us to see what's going on. So this will change from mobility to meals. It's rendering. And yeah, now a very strict linear relationship and probably not seeing an interaction, right? Because we don't see much of a difference. And so if we wanted to practice that, let's go ahead and do that. So we just did in our linear the year round. So let's add one more step. And then let's add in one more model or one more step or one more block. And let's add in the interaction term. And let's see what happens. And lo and behold, we see this new block, this new model, which added the interaction term. Look, the p-value was not less than 0.05. Therefore, what? Therefore, we can say there was no significant interaction. There's the interaction between year-round and meals is not significant. They're not influencing each other. That's what that means. Interaction means one is influencing the other. These two are not influencing each other. And in fact, we see, right, there's no change in R. R, in fact, didn't change at all by adding in the interaction term. Unlike in the previous example when we saw that there was a significant R squared change because the p-value was less than 0.05. Okay, and the assumptions look good here, even better, right? This is really fitting well along the QQ plot. Very good normal assumption of normality, and a pretty good random spread of residuals around the predicted values or fitted values of Y. And then here is our here's our regression output, our regression coefficients. All right, the final then is to say, all right, what if we don't know the general strength or the general order or what happens when we put in multiple? Let's start with correlation. Let's say what we wanted to do is we wanted to look at API and then all of the parent education variables. So that's percentage that didn't have high school, percentage that had some high school education, percentage of parents that had some college, percentage of parents that are college graduates, and percentage of parents that had some grad school. So I think 5, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 predictors, right? And 6 variables altogether. Okay. we're not going to do, we can look at this, we can practice the flex plot for a minute, but let's go ahead and look at the correlation and see how's that being rendered. So here's our correlation matrix. We see API, the academic performance is significantly correlated with all of these parent variables, right? And they're all, some are negative and some are positive. As the percentage of parents increases that do not have a high school, academic performance goes down. It's negative, right? As the percentage of parents, what is high school again? HHD, percentage of parents whose highest education level is high school graduate. As that increases, it also goes down. But as the percentage of parents who have some college increases, academic performance goes up. As the percentage of parents increases who have some who are a college graduate, correlation is even higher. Academic performance goes up. And then the highest it goes up even more if they've had grad school. And then here's all of the fun visualizations, which is great. I love that it gives us this cool big old correlation matrix visualization. It's pretty cool. Let's see how many we can do with the flex plot. I'm not actually sure how many variables we can add. Let's find out. We have API, and then we put in not high school, and we put in high school, and we put in some college. Oh, you can only do 2. So it stops at 2. So flex plot gives us some helpful information, but doesn't give us the full way of modeling all of the interactions. And that's one of the challenges of regression, is how to model all of this. So you'll do various pairs if you wanted to. You don't have to do it for your assignment. I wonder if we can panel by a continuous variable. All right, so we can get 3. I wonder if we could get more. Ooh. I guess flex plot. Ooh, can we add in 1 more? No, 2. So the most we can model is 4. So we can get an idea of what's happening when looking at API across 4 variables, across parents don't have high school grads, parents have some college, parents are college grads, and parents had some high school. So that's pretty cool. All right, and then let's do this stepwise to explore now. Let's put in all of these. So we wanted to put in not high school through grad school. So this group of 5, these will all go in here as predictors. They're all continuous variables, so they're covariates. And now what we're going to do is we're going to change from having them all come in at one shot, which is what we see here. They all came in at one shot. We're going to change this to stepwise. And now in stepwise, it does all of the modeling. It does all of this internally, so we don't have to do it. But we see here 5 blocks. And we can see the order. So the first block is that not having a high, as the percentage of parents increase who do not have a high school graduate, that is the largest predictor of academic performance. That alone is predicting 46.7%. And then the next one is adding in, did they go to grad school? Well, adding in going to grad school, that adds an additional 13.6. Now we can predict up to 60%. And then the next step is, did they have some high school? And then the next step is, did they have some college? And then the last step is, were they college graduates? So this is, by the time you get to the last block, you can sort of get the relative strength of of each of the predictors in predicting academic performance. And that relatively models well the standardized. When we get rid of this unstandardized and we put them all in the same unit of standardized units, we can see not having a high school degree, if your parent does not have a high school degree, that's almost 44% effect on academic performance. Right? We had that R square of 46.7, 46.7%. And that's about on the standardized, when you're thinking of standardized, the Z-score, it's about percentage-wise. So grad school is predicting about 35%, but then it drops down. If you have a high school degree, that's about 9%. Some college is 7%. College grad is 8%. And so this was optimizing. Now, how were these added and eliminated? None of them were eliminated. They were all found to be significant, but how were they added? Well, this is where we came down here to the method specification, and we just left it as the default. So the method specification is a predictor will be added if it leads to a p-value less than 0.05, right? That's the criteria we've been working with all semester so far. We've been thinking about hypothesis testing, that alpha equals 0.05, the 95% level of significance. And then it will be removed if that p-value was above 0.1. So all of these predictors had p-values that were less than 0.05, and so they were left in the model. As an example, I mean, if you wanted it, we could just have some fun here. We can bring in growth and meals and mobility, full, emergent, enroll. Let's just add those in and see. Do those also, are all of those included? No, there's not. There's a few that were not included. So we end up, the final set of all of those, the best set is meals, emerged, parent, is the school growing, how many are enrolled, and do the parents have some college? So you can kind of see what this does. Now, it's exploratory, might not make any sense to do it, but this is what stepwise is good for. It helps you get the ball rolling to start thinking about relationships among a lot of predictors and what might be the best set. So we had threw in there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We threw in there 11, and of those 11, there were only 6, right? Because model 0 didn't have anything in it. There were only 6 that were the significant predictors. And those 6 were right here. Meals, right? 1, 2, 3, 4, 5, 6. Oh, was it 7? 1, 2, 3, 4, 5, 6, 7. Yeah, 7 of them. Sorry, my bad. 7 of them were found. Yeah, 1, 2, 3, 4, 5, 6, 7, because 0 was the other. So 7 were found to be the most predictive of academic performance. Okay, well, that's it. That's the lecture for today. Your assignment is, I'll just make sure we're clear on what you're doing for the assignment. The assignment, you're going to do API regressed on year-round. the variable sum college and then do the year-round times sum college and do everything I just showed you in the first one, do the correlation, the flex plot, the hierarchical, so you can understand if the interaction term is actually significant. And then in the second one, do API on API regressed on all of the parent ones, year-round, meals, L, full enroll. And L is number of students who are English language learners, etc. And then interpret it and see what you find with. We kind of did it. There's a few that we didn't put in there because I knew you were going to do them for the assignment. So that's it. Just two things. And good luck. I think you'll do just great. If you have any questions, do not hesitate. Oh, you know what? I didn't share the screen. I'm sorry. Let me share the screen again. My bad. For the assignment, you're going to do API regressed on year-round and some college and the interaction term. And then the second one, I want you to do API regressed on that whole set of parent education one. I'll list them out. The year-round, the meals, English language, full credentials, emergency enroll. And make sure you understand what those variables mean. Meals is percentage of students receiving free meals. Enroll is number of students, so that's how many kids there are in the school. And emergency is percentage of teachers with an emergency teaching credential. Okay. Thanks very much. Bye-bye.